and I'm getting reports, not from this class, but generally within Utah, that things like access to data and lagginess on Microsoft Teams is an issue. Okay, because of this, the lecturers have discussed, and we have been strongly recommended that we use Teams for classes where it is required that there be interaction. For lectures, it's been recommended that we should record the lecture. This is to provide the ability for students who do not have reliable internet, or students who have laggy internet during the time of the class, that they are not disadvantaged with respect to the other students. So because of this, I have already pre-recorded today's lecture. Okay, so within my topic, there is topic 4 which is left, which is divided into 2 parts. The first part we definitely can finish today, and yeah, Lingeswaran, I understand, and not everyone is fortunate enough to have a fixed unified connection locally. Even those who do, if your neighbors or your housemates decide that now is a good time to download the entire series of Game of Thrones, then you are still going to be laggy. So rather than having to deal with these technical issues, then the pre-recordings are available. However, I think it is good for student discipline to have a fixed time, because just because there is a lecture for download does not mean you will download it, does not mean that you will actually watch. Okay, so to provide for those students, all lectures from here on will be made available, both here in Teams as well as in Webble. There's a Google Drive link posted up on Webble already in the class. I will also be playing the same recorded video for us. So this, if you do not want to view the video, or if you want, we can just sit here together. We will be going through the recorded video, and I will be present in case there are questions. Now, the thing is, when I am playing the recorded video, the sound that you are going to hear is the sound from the video, meaning the sound on my computer. Because of this, if any one of you unmute your microphone and start talking, that sound will also be played back on top of the video sound. Okay, I think I can cancel that, but so far I've noticed that there's been good discipline among all the students. You all are better than the lecturers, because when we had our faculty board meeting with the lecturers, there were about 20 out of 100 lecturers who had no idea how to mute themselves. Okay, so you're obviously more technically adept. So I don't think that's a problem, but if I do hear people sound during, then I may have to manually go and mute you all one by one. As the host, I have the ability to do that. I see that Ziheng and Roger got removed. I do not think anybody else has the permission to remove participants except me, and I definitely did not click that. I would wonder whether there's some connectivity issues. If it continues to be a problem, then let me know. After this class, we can try to debug this. Okay, so it's about 3:05 plus minus. We will start today's lecture. I'm switching over from my microphone input to the audio input of my computer, and I will play. I've divided this topic 4.1 into 2 recordings, both about 15 minutes each, so I'll play the first one first. Okay, before that, any questions from any students? Lingeswaran, there's not a question, there's a statement, and it's an untrue statement. Okay, if there's no particular question, let us switch over. Where is my... For topic 4.1, we're going to talk about automated work cells and computer integrated manufacturing systems. So the career that we're looking at is system design. This is not meaning that this must be a big company, but just a company which designs systems where you use automation. So we call this computer integrated manufacturing. This brings together the things that you have already learned up to this point. The implementation process for CIM involves 3 steps. The first is assessment, then simplification, then finally implementation. Assessment is the first step, where you assess what is the current state. What's the technology? Are your employees ready? Why is the current system the way it is? Are there historical reasons? Are there efficiency reasons? Is there political reasons where
Okay,
For topic 4.1, we're going to talk about automated work cells and computer integrated manufacturing systems. So the career that we're looking at is system design. This is not meaning that this must be a big company, but just a company which designs systems where you use automation. So we call this computer integrated manufacturing. This brings together the things that you have already learned up to this point. The implementation process for CIM involves 3 steps. The first is assessment, then simplification, then finally implementation. Assessment is the first step where you assess what is the current state. What's the technology? Are your employees ready? Why is the current system the way it is? Are there historical reasons? Are there efficiency reasons? Is there political reasons where there's power structures within the company? Once we have done this assessment, the step 2 is simplification. How do we remove waste? The point of automation, of course, is to increase efficiency, which means you must remove things which are unnecessary from every operation, every activity. And this requires you to define what waste is and where this waste happens. And in the implementation step, step 3, you have to build the system. And here you need performance measures, which means that when you are purchasing, when you are installing, you need to measure system performance. And what are the 2 requirements? Obviously, how much does it cost and how fast it is. That's the whole point of automation, that we want things to be fast and we want things to be much cheaper. So when we are doing automation, under automation, you have what we call flexible automation as well as fixed or hard automation. Under flexible automation, we have our manufacturing systems or cells, which are flexible in nature. And under fixed or hard automation, we have our inline rotary systems. So for production systems, on the one hand of the scale, you have projects. So we have talked about this in the first lecture, where everything is very manual and there's very high degree of specialization. You have job shots, repetitive, line, continuous. So the robot applications are more suitable in this region here. Okay, the region in the dotted line here. Why? Because once you have something which is very manual, that means there's nothing much which can be repeated, then it's not suitable for robotics, for automation. But if you have something that's very, very, very continuous, like a chemical line process, then also there's not much reason for robotics. You just put hard automation everywhere. So flexible automation, the priority is in this central area where you enable what we call agile manufacturing. Agile manufacturing is manufacturing which allows you to change, allows you to change order, change what is being made, and in essence to respond quickly. In the current situation, agile manufacturing is what allows a company which manufactures perfumes, for example, to start manufacturing hand sanitizers. That means that they can change the production line and it doesn't cost as much as redesigning a new new production line again. So this is the definition of flexibility. You can adapt, you can change and increase or decrease the number of parts which are produced in the system. You can accommodate routing changes, and you can change the setup rapidly using the same machines or systems without changing the systems. Okay, fixed automation, on the other hand, is basically fixed, sometimes custom made, sometimes off the shelf, but fixed automation where the whole point is efficiency. The whole point is as fast as possible, as cheap as possible. So the characteristics here is closed space productions. We really have to measure what is the flow rate, what is the travel time, and this is a sequential production process. Every station performs certain process steps, and we try to maintain a constant cycle time of each machine. This is for efficiency reasons. And in fixed automation, your raw material and components are introduced at various points throughout the system, and the number of stations is dictated by how complex your production process is. Because in fixed automation, we have to care about efficiency most of all, then the robots there must be much higher speed. And normally you only produce one or a few products. So that's your comparison between flexible automation as well as fixed automation. Next, we will talk about the design of a cell within your CIM. And what is a cell? Basically, that whole group of machines, which is the robot, which is at the center, and all the other machines which the robot directly works with. So we call this a robot cell. The design of the cell is how we lay out the machines and everything on the floor. This is important to ensure efficient operation, meaning operations where your utilization is maximized. How often the robot is doing something useful. To do this, we need to have an idea of the design sequence. Okay, this is the set of sequence of tasks which should be followed when you are designing a robot work cell. So there's a flow chart here by Asphalt in 1992, which has a 5-phase approach for implementation of a robot work cell: planning, development, mock-up and testing, installation, production, and follow-through. Now, there is a primary flow where we follow through all the tasks sequentially, and if you skip any of the tasks, then this can result in the abortion of the entire installation, failure. Okay, it's possible at each stage to reconsider. So when you are going, for example, to mock-up and testing, then you realize that something went wrong in your development, then of course you have to go back. Okay, but your primary flow is still going down this chart, and when you are doing all this development, you have to plan for every eventuality, and your final result, which you are trying to get, should be as robust and reliable as possible. Because the further along you are in the implementation, the higher the cost of trying to go back and change things. So let's look at the stages. The planning stage should involve whatever engineering personnel, union representatives, means representation for the workers and the labor force. And the first stage can be further subdivided into certain tasks. Now, I'm not going to read out all of the tasks here, but basically the whole idea is, where can we automate? What makes the most sense to automate? If we want to automate, what type of changes do we need to make? So all of this we are planning. Okay. Then what is the application? What is it that we actually want the robot to do? So isolation of the application requires studying the current manufacturing operations. So currently it always starts with manual. What is this worker doing? What is that worker doing? And this is why you need them to be inside the discussion as well. And the tasks involved in the applications will help the designer to decide, oh, this task is primary carrying. This task is primarily operation of a certain tool or a certain set of tools. Typically, your industrial applications, there's a whole list of things. You are all engineers, so you do not need me to explain one by one each of these. When we are talking about the application, we also need to look at the performance characteristics that influence which robot arm or what type of robot arm, what specifications we are looking at: the payload, work volume, speed, repeatability. Other considerations include, oh, do I need a hydraulic drive system because I need power? Or wait, this is a clean room environment. We are producing things for hard disk or silicon-based products. So we cannot use this particular type of robot. We need a clean room robot. We need to spend more on that. The task also determines, as we have talked about in the previous lecture series, what is the in effector? What is the gripper? What is the type of system that we need to use in order to actually do our work? And then the next step after this is considering the possible benefits of introducing a robot cell and the drawbacks. Now, sometimes it can be the case of, yes, definitely we are introducing, but it is always important to consider whether or not this actually makes sense from a financial perspective. Will it make things more efficient? Will it save time? So why does the company want to introduce the robot work cell? So there's all this, which is basically all of it comes down to money or the earning of money. Okay, even things like improving working conditions primarily is so that you can keep your staff, because hiring new staff and training new staff is very expensive. Primarily is if your staff are happy, then you're less likely to get sued. Each of these reasons can be used to describe what is our objective, and we should be cautious when stating the project objectives. If the project objective is just let's remove the workers, this becomes very difficult to justify because you need the workers' cooperation. And if the worker is saying, oh, I am going to be replaced, then he has no reason to cooperate, and the effect on your production might be very negative, both in the near and the long term. So there's more discussion on this is in the appendix. So what are the possible drawbacks? We will look at a few of them. If you introduce a robot, this influences not just the individual worker, but the whole manufacturing operation. It could be something that's beneficial for the company, but the employees are unhappy with. It could be something bad for both companies and employees, or more likely, it can be bad for a certain employee, but good for most other employees. So if there is a particular bottleneck, then that person may be getting replaced or reskilled to another area, but it could be that the other employees now receive better inputs to their tasks. So ideally, of course, we want something that's good for company and all employees, if it's possible. Now, we also need to consider whether retraining or reskilling the employees to new roles in the company can be beneficial both to the company and to the employee. Now, the removal of hazardous tasks is one of the most obvious places where we can have the situation which is good for company and good for employees, because hazardous tasks, obviously, life is much harder to replace than any amount of equipment. Okay, so this is also beneficial to company because sick leave is one of the factors in affecting productivity, which is very high. Right now, we are on a movement control order. A lot of things cannot be produced unless you have workers on the floor. If you have a fully automated system, however, then you would not actually need many or any workers at all. And so when you have a pandemic, you can continue to produce. Whether you have a market or not, that one, not sure lah. Okay. Now, what are the potential barriers to automation? There's a huge list of potential barriers which we are going to look at here. What is the technical risk? Can it work? Might it not work? What's the variability? Would your system what is the technical risk? Can it? Okay. Now, what are the potential barriers to automation? There's a huge list of potential barriers which we are going to look at here. What is the technical risk? Can it work? Might it not work? What's the variability? Would your system need to cope with a lot of different changes? Of course, robotics tends to have a high initial investment, so you need to look at the payback period. How long before you get your return on investment and before it becomes profitable to install this system? Health and safety concerns. Do you have sufficient skills within your company, or can you hire such skills? What is the floor space required? Will it affect your company culture as well as the working environment? So we will pause here and then I will start another video to continue this series. Okay, who is the one who's playing with the mute button? Okay, so this is the first half. We'll take a few minutes break. Now's a good time if you want to take your toilet break or whatever. If there are any questions, now is also a good time to put the questions either in the meeting chat as well as using your mic. Yes, for those who came in later, I am playing a recording. It is my voice, so yeah, it's a recording. This is the same recording I made available for download. The reason why we are using recordings is because not everybody has high-speed internet, and with the extension of the lockdown, it is likely some people will run out of quota as well. Okay, so the downloads are very small. I think this particular first half lecture is 17 meg. The second half is 20 plus meg. So should be able to afford. It takes much more data to be streaming your Microsoft Teams. So for those who have such restrictions, they don't even need to come for the Microsoft Teams if they do not want to. Of course, the flip side why we are still running this class is because of discipline. If you have a class, you come, you listen. If you don't have a class, you try and remember to watch the video. You might just keep the video in your computer the rest of the semester and never open it. Okay, so yeah, the point of the video as well is I am going through quite quickly, prepared so that the video becomes shorter. Because once I'm putting a video for upload, I don't want the video to be 1 hour class length. That's not fair for everyone who is downloading and watching. Now, I've already received email requests permission to download the video. For various reasons, this video should only be accessible to Utah students. Okay, not that I think anybody outside Utah really want to hear my voice, but so it is hosted on our Utah Google Drive. You will need to log into your Utah Gmail address, your Utah Google account to download from Webel. Okay. Alternatively, if you want to download from Teams, I also upload to Teams, then you can download from Teams. But I have noticed quite a few problems students downloading from Teams. Okay, so up to you which one you want to do. If you are downloading from Webel, make sure you're logged into your Utah Google account and it should be fine. Any issues with downloading, please contact me. I will try to either help you solve or forward to IT and see what can be done. Okay, so this is the lectures for 4.1. 4.2, I'm still working on it. It will be up before Friday. So by all estimates, by this Friday, my lecture slides will have been finished. Okay, which have already been uploaded, the PDF itself. The recordings should be done and you will be able to hear them by this Friday. And then I will hand over back to Dr. Lee and we will finish the subject. Okay, any questions up to this point on the administrative aspect of the subject? Okay, if no questions, let me load up the other video. Let's see, correct video. Yes, correct video. Okay, I said 5 minutes. I will let the proper 5 minutes expire. So in case someone is doing their business in the toilet, they have time to come back. I should download the Utah theme song and play it during the break, now that I think about it. Okay, so if we are ready, let's go for the second half of the lecture. This is the second recording in the series of automated work cells and CIM system, and I will just continue where I left off. We will need to look at what the current operation is. We try to document what is currently being done, and so it's basically the task that the robot will be tasked to do. That is what we are looking at. This documentation should include what's the layout, how long different cycles takes, because the robot is not the only one working. There's some production machines involved as well. How long would manual operation take? If your robot cannot be faster, significantly faster than the person, then it doesn't make sense. What is the record of quality? Where is this a type of task where the human manufacturing has a high error rate? Okay, so what are the problems with the current manual methods? Can these be solved, or will that be made worse by automation? Now that we have this, then we have to look at what is a suitable robot, and is this robot work cell suitable as well? So we are looking at payload, work volume, speed, repeatability, and then we have to consider, will this be something that needs to be very flexible, meaning short product life, you know that you need to change this in a couple of months, or if your product life cycle is long, you are manufacturing a type of vacuum cleaner which will be the same 4 or 5 years from now, and you just need to continue to churn them out, then maybe hard automation may be a better choice. And there's a simple graph which shows the relationship between production rate and unit cost, and where it makes sense to use manual methods and where it makes sense to use robots for flexible automation, where it makes sense to use hard automation. Generally speaking, you will find that when you are using a manual method, the cost for each unit is maintained. For a high production rate, you just hire more, but your cost is by and large maintained. However, increasing the production rate of a hard automation system reduces the unit cost because all processes are automated, so doing it again and again, not a problem. For robot systems, however, flexible automation, there is a non-linear reduction. And this non-linear reduction, we will go back to the graph here, basically indicates that, okay, now we are improving our unit cost, and then at one point, this is the limit to what one robot can do. I need to buy a second robot, or I need to increase the size. Then there is an increase in cost, which is reflected in the increase in unit cost. And this happens again and again and again. However, your unit cost will tend to be less than a hard automation system at lower production rates. Of course, if the production rate goes high enough, then there's no way a flexible system can beat a purpose-built system. Okay, so robots are normally used in mid-range production rates, where you have a bit higher in capital investment, but your unit cost ends up lower than a hard automation system and a manual system. So manual production is the default because your initial capital investment normally is very little. Okay, you just need to hire, and there's not much initial capital. Hard automation has a high initial capital investment, but the reduced unit cost normally makes it worth it if you know that your product will be in demand for a long period of time. So once we have made these decisions, what's our layout? The current layout of how your factory floor may be, maybe you have to modify it. You might have to change the conveyor system. You need to reroute things. The interaction of the robot with the conveyor system is one of the important things you have to consider. The robot has a fixed, you want the utilization of the robot to be high, and so you want something to always be waiting there when the robot is going to continue. So you need some type of buffering, unless you have a just-in-time system where it comes and immediately the robot is able to do. The problem in such systems is if the piece is late, for example, there was some filtering before it gets to the robot might be underutilized. There will be a period of time where it's not utilized, and this of course increases the relative cost of running the robot. So the complex iteration of all these parameters means that this is not something that we can 100% design from the start. So we normally use an iterative approach. So the iterative approach is basically, okay, let's design first. Maybe it will look something like this, and then we will test it out. And if we test it out, then we find, oh, I find that the robot is waiting a lot here, or I find that my buffer here needs to be increased. Then we change that, and then we see, oh, how does this work? Now, this iterative approach can be done physically, but nowadays, with robot simulation software being quite good, we want to simulate these things in software. The benefit of this is, of course, if we can do it properly, it is much, much cheaper than having to install things and then move things around physically. Okay, so there can be simulation packages which check for collision, for timing, and where you can do the programming on the machine and run the same program which you will run on your production machine and see what happens. So most robotic companies, as part of their contract, when they sell the robot, will provide the CAD files of your robot with all the dimensions correctly. So you just need to import it into your simulation software. And regardless of which system you're using, there's normally a standard work cell layouts, because nobody wants to draw things from scratch. So you put it together in a standard cell layout. Now let's customize this for what I want to do. What is my application? So one of the standard work cell layouts will be a radial layout. The nature of your 6 degree of freedom robot means that where it can reach, the primary reach area tends to be a donut shape. And so if your workpieces, if your workstations are in a donut shape around the robot, then it tends to be beneficial for the robot in terms of efficiency. So you can see this on the slide. You can move from position to position, and this is the most efficient. Okay, so the reason for this, of course, is that your waist joint is radial, and if you arrange all the machines in a circle, then this is good. Okay, so this is a radial work configuration for the machine of truck differentials where the robot is doing different things. So you have your A, B, C, D, E going counterclockwise. Oh, this is where the parts come in. This is where it does this particular operation and that particular operation, and this is where you deposit it, then it will go out. So this uses a radial layout, as we have mentioned, around your cylindrical robot, and anti-clockwise travel. You may have within this layout some smaller robot cells. Okay, this is as well possible. So this example for assembling electrical motors, and the arrows show, okay, it comes in from the right and then it's going. The main robot, the big one, would be transferring the workpiece, and then there is a smaller robot which is perhaps combining a second part for the assembly, and then the big robot will bring it to the second smaller robot which is also doing something similar. So these radial layouts can be combined together with some overlap, with proper design, of course. It is important that if you are combining different robots together, that your jig can be reached by all the robots, obviously. And this layout often includes feeders so that the operators can access the jigs without having to enter the robot cell, because every time you enter the robot cell, there is a safety requirement, which means that you will have to stop the robots, which is bad for production. So this is an example of your jig and your fixture, which you will use here. So radial layouts are good for the robot, but they are hard to design around, because like if you have a plate and a lot of donuts, you realize that there's a lot of inefficiency when you're putting the donuts next to each other. And so generally inline layouts tend to be more efficient in terms of their usage of space. And these are more suitable as well if you have a Cartesian robot or you have robots on rails, so that you have your inline conveyor and your robots are to the side. Okay, so this arrangement is suitable when your accuracy is not very critical. This arrangement means where you are mounting the robot on a linear array. Okay, so you have an extra degree of freedom, or your robot is tracking the movement. So if you have an extra degree of freedom, then the robot itself is moving. But if your robot has to track, then you must realize how the work volume interacts with the conveyor. And it's not equally easy for the robot to access different ends of the conveyor. Okay, so this is one of the disadvantages using a cylindrical robot with your inline layout. Okay, so the work volume that's available is reduced. So your robots are frequently working on the parts which are on the using the conveyor, so that the robot can be moved such that the work volume will be appropriate for what the robot is currently doing. Another further consideration is, will you collide? And you can see that the work volumes are overlapping. Therefore, there's always the possibility of collision. Now, you can avoid collision using sensors, but that is inefficient. So you need to very seriously look at the overlap timing. What is the timing for interaction between the robots, such that they are all able to do their work without any collision? And this is actually where your simulation software is really, really helpful. Now, of course, other robot cell layouts exist. Most of these are just variations on these themes. In this system, you have added a fence, something like what we see in our lab, because safety is a major consideration when you are designing a robot work cell. Okay, so we have talked about this in the lab. I wouldn't repeat what I've been telling you all in the lab. So the development part, then we have to see about, oh, how can we develop the hardware, the pieces, the handling equipment, the processing machines, everything that the robot is interacting with. To reduce the possibility of problems, we have to look at the worst case scenario. What is the worst that could happen? Could this have a different orientation? Could it fall? Could it be redirected? Could the tolerances be way too loose? And once we have talked about all this, then we have to have a mock-up. Something similar, a physical system similar to what we will eventually have. And we are using this to evaluate the robot program. So there's a bit of a Murphy's Law thing going on here. Whatever can go wrong will go wrong. And the reason we do mock-ups is because the mock-ups will be with cheaper equipment. So any damage will be to the mock-up and not to the actual expensive machine. In addition, during the transition, we sort of improve the chance that the machine will be ready to go straight away. and that you would not have to do much commissioning using a mockup. Okay, so facsimile here means just copy. Okay, the positioning of sensors, the redesign of the cell through addition of different sensors, perhaps in your mockup and your testing, you find that there is a high risk of a certain type of collision, and you want to include sensors to prevent that from happening. That is something that you can find in mockup, which is a bit harder to see in simulation, because as good as simulations can be, you are not physically there. It is not something that you are physically seeing. So experimentation also permits a familiarization. This is on the human side. The operators who have to work with the robot can look at the mockup and have an idea this is what is going to happen. In most cases, just like we did in the lab, our initial trials are carried out at a slow speed, and then at full speed, when we have completed the programming, now we run it at full speed. Once we have done all of these preparations, the final step is installation and production. And in the installation, you normally have a pilot production run where it's exactly the same as what the mockup has done, but this is the final installed system. If it's not possible to do a pilot production run, then normally what you do is you only upgrade half the line so that there is continuing production. And once in production, then this is not job done. You have to continuously evaluate what, based on your objective, have we achieved this? Have we saved this time? Have we saved in terms of your efficiency? Have we saved in terms of the rate of discarded parts? Has all of these things improved? Okay, so this is our brief 2 recordings on the first part of topic 4. There are a few references here. This is of course the textbook. You remember that we quoted this guy earlier. There is an IET standard, a guide to installing industrial robots, and there's quite a few other things that you can read. So there are links which are given at the top of the slide. This link here, and the summary of the content is here. So for example, in our first appendix, we are talking about the advantages and disadvantages of automation, which is what we did right at the start of the lecture series. Here, on appendix 2, we have another list of advantages and disadvantages from a different perspective. On appendix 3, advantages and disadvantages of using industrial robots, and this particularly with respect to cost. And in appendix 4A, 4A and 4B are from the same website. This one is why you should use robots and what they are good for, what they are useful for. Okay, but then in 4B, why you should not use robots, or why the use of robots should not or won't eliminate your manufacturing jobs. Okay, so this talks as well about reskilling and things like that. Okay, and of course in 4C from the same website again, we are talking about how robotics can make economic sense, can make your manufacturing much more competitive. You will have lower price, better quality, things like that. We talk about the economics, the ROI. Finally, in your IET standards, your guide, this is the zone. This is a similar graph to what we saw earlier. This is the zone between your units per model, which is basically your production rate, as well as your production throughput, as well as how many units the unit cost is. So in this case, it's a number of models, short lifespan, which is correlated with the unit cost. So that's the end for this set of lecture slides. Okay, so that is our topic 4.1. Any questions from any students? Okay, so let's take questions on the topic first. Then the administrative things I will cover once we are done with the subject matter. Prasaf, what's the question? Prasaf, are you there? Okay, that's a good question actually. I will refer you back to the, let me figure out which slide it was on. Okay. No, so I know it's the last slide. Let me reshare my screen. Okay, so this slide, which is slide 9, shows basically a different version of the same thing, and our dotted line here shows which area is suitable for robotic applications. Okay, so hard automation is still automation, but when we are talking about robotics, hard automation may use robots. It's entirely possible, but a lot of times it's more cost effective and faster to not use what we would typically define as robots. So it can be something as simple as, instead of using my full 6 degree of freedom robot, because the big advantage of a 6 degree of freedom robot is that it is 6 degree of freedom. We have full flexibility. There's a lot of possibilities to what we can do. We can change the head. Okay. Instead of that, I could be using just a Cartesian 2 degree, 3 degree of freedom robot, because the only thing I need to do in this part of the line is that one task. Okay, so that is hard automation. But of course, that means that this section of my production line only can do this one thing. Whereas in a more flexible, something in the middle of the graph, where we have our repetitive or line production systems, then our robotics makes a lot more sense. The KUKA robot that we see, these type of robots make more sense in the middle. When you want some flexibility and you are not prioritizing the low unit cost and high production rate above everything else. Okay, so that is basically this graph, which I'm showing on the slide now, is similar to, in this thing, your IET standards, what we call the robot zone. Okay, by robot here, it is referring to our robotic arms. Not just robot here doesn't mean any sort of automation. Okay, hopefully that answers your question. Please follow up if you need follow-up question here as well. I also see another question from Shensan. Appendix got included in final. Not sure what exactly that means. I would never ask a question that looks okay. So let me go back to that slide. I will never, no lecturer is going to ask a question saying, in this website, what do they say? Okay, that is not reasonable to ask. That being said, the appendix is additional information and reading which can help you to answer. As you have seen from your mid-semester, we do ask questions testing your understanding. Okay, so having read the appendix can help in that. But the flip side is, if it's not within the topic and subject matter, then it's not really necessary. That being said, the way we design based on our course outcomes, just the materials which are provided are sufficient to do the entire final exam. Additional information can be useful, but it's not necessary to do final exam. Okay, if there's any further questions on that, Sensan, please do ask. Also, any other persons got further questions? Can use the mic or can chat, up to you. Okay, if not, then there was a question on the midterm. I will postpone that discussion on midterm until the uni announcement on Friday. After the university announcement, I can tell you there will be much more clarity, so it will make much more sense. Okay, nobody will be disadvantaged as far as we can arrange. What tutorial on Friday? Same tutorial as was on this morning. So Friday evening will be the last round where we have this tutorial for. Then we will move on to the next tutorial next week. Dr. Lee will take over. Any further questions that doesn't involve Schrodinger or anything? Okay, if there is no more questions, thank you for attending. We finished a bit earlier because obviously recorded lectures are much faster than me reading out and trying to explain live. So, tutup kedai, please leave the class and let me try and find out why is it that people are allowed to mute me. This doesn't seem very positive. Okay, so thank you very much. I will see you all on Friday for lecture again. Stay safe, stay healthy, and wash your hands. You are welcome all.